All right, we are going to do AP number 3. This is at the bottom of the page, and if you flip to the back of your packet, that's where it is. Now, this is the 2006 Mechanics 3-1, and we're going to do part A and B two ways. So this first video is going to do it with forces and torque with a 1D motion problem. The second way on video 2 is going to be with energy in a 1D motion problem, and then you can choose which one's going to be best suited for your abilities. So it starts out with a ring starting at the top of an incline, angled theta, length L. They give us the moment of inertia for a ring, and it's going to roll down, and it wants us to figure out an equation for the acceleration of that ring for part A, and it wants us to figure out the velocity at the bottom for part B. So first we're going to start with the idea of torque and forces. So because the object is both rotating and moving, I'm going to do both a torque equation and a force equation. Okay? Now, with these two equations, we're going to have some common themes, namely the angular acceleration and the linear acceleration of the center of mass are going to be related, and that's because it's rolling without slipping. Okay? So the velocity of the center mass is going to be equal to omega times the radius of the object. This acceleration of the center mass is going to be alpha times the radius of the object. Now we do need to make sure that both our A and our alpha are both positive. We don't want one to be negative just because it's rolling down clockwise. Okay, so we'll make sure of that, and we'll also kind of make this connection between our linear acceleration of our center of mass and our angular acceleration of our object. So since we're doing torque and forces, we're going to start with a free body diagram. So remember, with rotation, with our torque equations, we really care about the location of the force. Okay? So here I have friction acting at the surface on the edge of my ring, and it's going to oppose the ring. You're kidding me. Hold on. It's going to oppose the ring sliding down the incline. Okay? So then I have gravity acting at the center of mass, pulling it straight down, and I have the normal force acting perpendicular to the surface. So that's the location of those forces. Now, two of these forces are not going to produce torques about my axis of rotation in the center here. The normal force is not going to produce one because the normal force is parallel with the radius. Okay? And the gravity is not going to produce a torque because it's acting at the axis of rotation, so its lever arm is 0. So the only one actually producing a torque is the force of friction. For our linear free body diagram, just think about a block on an inclined plane. So we got friction resisting it from sliding down. I got gravity acting down at an angle. I will have to resolve it. And then I do have my normal force acting perpendicular to the surface. All right, we'll move the camera here for a second. Okay. So now we're going to set it up. So here's our rotation problem. So we're going to sum up the torques, set it equal to I alpha. So I did have that force of friction. Let me use a black marker. I do have that force of friction acting at the radius. And because we want our alpha, ooh, the camera's still moving. There we go. Because I have that force of friction acting at the radius, it's going to be force of friction times radius, and they're perpendicular to one another, so I don't need to include a sign or anything. I have I, which is mr squared for our ring, and then I have alpha. Okay, but we're going to make the substitution that alpha is that centripetal that center of mass acceleration divided by the radius. Okay. The reason we want to make that substitution here is what happens is if my location where my torque is being applied and my rolling object, everything's going to have the same radius. We're going to cancel stuff out. And so I'm left with the relationship that the force of friction is equal to ma. Okay. And I'm going to need that when I plug that into my linear problem down here. So in the linear problem, I have mg sine of theta acting down the incline. I have force of friction acting up the incline. I'm calling down the incline my positive direction, is equal to ma. All right. So I just learned force of friction was m times a, so I'm going to have mg sine theta minus m times a equals m times a, you're going to see that I do have an m in all my terms, so I get to cancel that out. Move this a over the other side, so I get 2a. And then I can divide that 2, so I get g sine theta equals a. But I had 2a, so I'm going to divide that 2 over, and I get this. So there is part A of that question. For part B, we're going to go ahead and, because our acceleration is constant, because the angle is not changing, nor is gravity, I can do a constant acceleration problem. So I set up my variables. It starts at 0 meters, ends at the bottom of the ramp. Length of my ramp is called L. It starts at rest, and the acceleration I just got was g sine theta over 2. Now, I don't want an equation with time. I'm trying to find the velocity at the bottom, so I'll pick an equation without time. You can look at the sideboard. We're going to use equation number 1. So the final velocity squared is equal to the initial velocity squared plus 2a times the final position minus the initial position. Cross out anything that's 0, and I'm left with the velocity is equal to the square root of 2a times x. Substitute in my variables, so I'm left with v is equal to the square root of, and you'll notice I'm doing 2 times a, so 2 times g sine theta over 2, the 2's cancel out, so I'm left with g sine theta times L, all underneath that square root. And there is part B.